All right, now let's talk about how to find the oxidation number. Now remember that the oxidation number is a measure of charge. It tells you how charged each of the atoms is in the compound. And maybe we should start by comparing this with the formal charge, because you know that formal charge is also a way of measuring the charge of the atoms in the compound. So why do we need two different methods? Well, they're based on different approximations. Remember that all of the bonds in a molecule are kind of intermediate between covalent and ionic. Nothing's perfectly ionic or perfectly covalent, but they're kind of they're intermediate between them. Well, if you approximate all the bonds as perfectly covalent, then that gives you the formal charge method of figuring out charge. And if you approximate all the bonds as perfectly ionic, that gives you the oxidation number method of figuring out the charge. So let's look at an example to see how that works. So let's start, just for review, let's do the formal charge method. Formal charge is what the charge would be if all the bonds were perfectly covalent. Formal charge is what the charges would be if all of the bonds were perfectly covalent. Now, first of all, how many electrons would a free oxygen have?
6.
Good, because it's in the 6th column from the left of the periodic table. Since oxygen is in the 6th column from the left of the periodic table, the free oxygen has 6 valence electrons. And how many valence electrons does a free hydrogen have?
1.
So these are how many electrons they would have if they were free. Now let's figure out how many electrons they have in this molecule of water. Well, remember that we're going to do the formal charge. And formal charge is based on imagining that all the bonds are perfectly covalent. What does that mean? We should imagine that all of the electrons are equally shared. The electrons are being perfectly evenly shared between the two molecules, between the two atoms. So for example, since there's 2 electrons in each bond, if there was even sharing, then one of the electrons would go to the oxygen here, and the other electron would go to the hydrogen. And in this bond, one of the electrons would go to the oxygen, and one of the electrons would go to the hydrogen. That's what it means to imagine that the bond is perfectly covalent. It means that there's perfectly even sharing of the electrons. So one electron goes to one atom, and one electron goes to the other. Well, if that was the case, how many electrons would this hydrogen have? Well, notice that in the circle, there's 1 electron. So this hydrogen here has 1 electron in the molecule, which is the same as it would have when it's free, so it has 0 formal charge. It has 0 formal charge because it hasn't gained or lost electrons. It hasn't gained or lost electrons, so it has no formal charge. And how many electrons does the oxygen have? 6. 1, 2, 3, 4, 5, 6. So what would its formal charge be?
0.
Because again, it hasn't gained or lost electrons either. And this hydrogen, again, has 1, so its formal charge would be 0. And notice that if you add up all these formal charges, they give you an overall charge of 0, which matches that we know water does have an overall charge of 0. Okay, that was just a quick review of formal charge to show that formal charge is based on imagining that all the bonds are perfectly covalent. Now there's some, usually when people learn this, they just learn a formula, something like number of valence electrons minus number of electrons in the lone pairs minus 1 electron from each bond or something like that. But I think it's simple enough to do this with the circles, and you have much more intuition for the way the method works. Okay, now this isn't too important here, I just wanted to do this for review. Now that's the formal charge method. Now remember, this was just an approximation, because are these bonds really perfectly covalent? Well, no, because who wants the electrons more here, the oxygen or the hydrogen? The oxygen, because it's more electronegative. So this is just an approximation. In reality, these 2 electrons should both be closer to the oxygen than to the hydrogen. By the way, while we're at it, you know that generally something is more electronegative if it's further to the right in the periodic table, and also if it's further up in the periodic table. There's one exception to that, though, which is hydrogen. Hydrogen is a pretty important element, and you can't tell how electronegative it is from the periodic table. So about how electronegative is hydrogen, what element is hydrogen similar to in electronegativity?
Helium.
That might seem like that from the periodic table, but the periodic table is actually misleading that way. After all, helium has almost no electronegativity, right? Because it's a noble gas. And hydrogen actually isn't like that. Hydrogen actually really wants to gain an electron. So it turns out that hydrogen is pretty much in between boron and carbon in electronegativity. Hydrogen is very similar to carbon in electronegativity. Carbon and hydrogen both want electrons about the same. Carbon is slightly more electronegative than hydrogen, and boron is slightly less electronegative than hydrogen. So for purposes of electronegativity, you should think of hydrogen as being kind of on the border between boron and carbon. So the periodic table is misleading for hydrogen. Okay. So again, it has some willingness to gain electrons. It also has some willingness to lose electrons. Okay, so now let's think about oxidation number.
So that's even true if it's in the D block as well, for electronegativity?
Well, in electronegativity, generally speaking, actually the electronegativity trends for the D block are a little bit complicated. The trend that I've been talking about here is mainly for the representative group elements. The further you are to the right and up for the representative elements, the more electronegative you are. But there's a bunch of exceptions to that for the transition metals. The most important thing here is that transition metals will generally want electrons less than these nonmetals over here. That's what is most important for that chapter. Clearly, the transition metals want the electrons less than the nonmetals. That's why in the coordination compounds, the transition metals always end up with positive oxidation numbers, and the ligands end up with negative oxidation numbers, because the ligands are taking the electrons away from the transition metals, because the ligands are all nonmetals. Things like fluorine or iodine or nitro groups or ammonia groups or whatever. Anyway, going back to oxidation number, so let's think about water again. Now the oxidation number approach is when we approximate all the bonds as perfectly ionic. We're approximating all the bonds as perfectly ionic. Remember that formal charge was when we approximated the bonds as perfectly covalent. Remember that perfectly covalent is when the electrons are evenly shared. So what's the opposite of that? What does ionic means? It means that the electrons are completely transferred. Well then, who would these electrons be transferred to? The oxygen or the hydrogen?
Oxygen.
Because it's more electronegative than hydrogen. Here's where we use what I was just talking about over here, that we need to know the electronegativity of hydrogen. Hydrogen is to the left of oxygen, if we know that hydrogen is about electronegativity like carbon, so the oxygen wants the electrons more. So in this model, we're going to assume that both electrons are owned by the oxygen. And how about these electrons? Who should these be owned by? Also the oxygen. Okay, well, so in this ionic model, how many electrons does this hydrogen have? 0. And how many electrons does the oxygen have?
8.
And this hydrogen has 0. You can see we get very different results when we use the ionic model as opposed to the covalent model. So is this hydrogen going to be relatively positive or negative compared to when it was free?
Positive.
Because it's lost its electron. It used to have an electron, and now it doesn't have that electron. Losing your electron makes you positive, so this would have a positive 1 charge, positive 1 oxidation number. How about this oxygen? Should this oxygen be positive or negative?
Negative.
Because it has more electrons than when it started. It's gained electrons in the molecule. The whole point of oxidation number, again, is to ask what's your charge relative to when you were free? Well, this has gained electrons and become negative. How negative? What would be its overall charge? -2, because it went from 6 electrons to 8 electrons. So this would be -2. And what would be the charge on this hydrogen?
+1.
And in that case, what would be the net charge on the entire molecule?
0.
+1, -2, and +1 adds up to 0, which it has to because the overall charge is 0. So that's always a good way to check whether you're doing oxidation numbers and formal charges right. You should always add them up at the end and make sure they add up to what the overall charge of the species is. Well, for a neutral molecule, they have to add up to 0. Okay, so this is a good example of the difference between formal charge and oxidation number. One of these is based on assuming ionic bonding, and one is based on covalent. Which one's right? Well, neither is perfectly right, because remember, the real bonds are intermediate between perfectly covalent and perfectly ionic. It's just that sometimes one is more useful and sometimes the other model is more useful. Well, when you're working on redox reactions, this is more useful, because redox is about transferring electrons. So you couldn't think about redox reactions in terms of formal charge, because in formal charge we pretend that the electrons are not being transferred. So we should use this approach if we want to focus on the electrons being transferred. So that's why in this chapter we're focusing on the oxidation number approach.